Hello everyone, welcome back to all of you on my YouTube channel. I'm Ankit Mishra. I am teaching for GATE Chemical Engineering for since last 5 years. I have started this lecture series for process transition control in order to keep the motivation for GATE 2026 and BARC 2026. And also this lecture will be very much helpful for the person who is appearing for the interview in NPCL and BARC 2025. Okay, so here in the previous lecture I have discussed about the transfer function for CSTR, and there we have seen that rate of reaction was like that, and after that we have performed the material balance for CSTR, and after performing the material balance for the CSTR you can see that we have taken the Laplace transform for the equation first from here, and after that we have converted this into S domain, and from S domain you can see that concentration of A at the exit is in S domain divided by concentration of A at the inlet in S domain, that is called as the transfer function for the CSTR. And here you have seen that we have got the equation is 1 by tau s plus k tau, right? So in GATE 2025 we have seen these kind of numericals. After that I have also derived plug flow reactor transfer function for the plug flow reactor for the first order reaction. And here you can see that whenever we are talking about the plug flow reactor, the concentration of the reactant and product changes at the with respect to the along the direction of the flow or along the direction of the length. So here you can see when we perform the material balance in the plug flow reactor, we obtain this equation first, del Ca by del T plus U del Ca by del T del Z, that is equals to minus Kca. Why? Because Kca is the rate of reaction, and after that U del Ca by del Z is convection term, and del Ca by del T is the rate of change of concentration with respect to time, and concentration also changes with respect to the space. That's why del Ca by del Z term will be there in plug flow reactor profile. And how we are getting these things, you can I'll be talking this material balance in a chemical reaction engineering, but try to understand these things right now. And when we take the Laplace of equation first, since this is a different ordinary differential equation with respect to the time, so you can convert this T domain to S domain, and once you convert these things, again you have left with the differential del Ca by del Z, and again this becomes the ordinary differential equation in Z domain or Z. And once we integrate the equation second from here, and we can get this kind of transfer function. So this is all about the transfer function of plug flow reactor, and mostly they can ask this kind of question only. So today I am going to talk about the transfer function of the liquid level. This is also very important. Right, so transfer function for liquid level tank. So right now I'm just going to talk about the simple thing that, let's say we have a tank, something like that, liquid level tank, and material flow rate is, let's say if I'm assuming flow rate is Fi and density is rho, and here it will be in meter cube per second, that is the volumetric flow rate, right? And at the exit you can see that there will be a valve, right? And this valve is having some kind of resistance, and this will be outlet flow having F, that is in meter cube per second, that is the volumetric flow rate, and density I am assuming the constant density system, density is not going to change, right? So this is our liquid level tank, something like that. Okay, so now let's say I am assuming this tank is filled with a liquid, something like that, with the height of h, right? So I am assuming the height of the liquid in the tank is h, and the cross sectional area of the tank is A, right? So this one is the cross sectional area, and I'm assuming is A. And now if I'm talking about Fi is the inlet flow rate, inlet, and what will be the unit in meter cube per second, and what is F, that is equals to outlet volumetric flow rate, and obviously this unit will be in meter cube per second. Okay, and now if I am assuming A will be the area of cross section of the tank, and that will be in meter square, and h is the height of liquid in the tank. That is a bit confusing thing. This is not the height of the tank, this is the height of liquid in the tank, height of Okay, so till now we get to know what is the significance of all of these variables in the problem. Now if I the mass balance, if I apply the mass balance here, so you will get, so I can write rate of mass flow in minus rate of mass flow out. This is simple. That is equals to accumulation or rate of, right. So volumetric flow rate is already given. If I'll multiply this volumetric flow rate with these things density, that will give you the mass. So I can write rho Fi minus rho F, that is equals to obviously d divided by dt of mass in the tank. And what is mass in the tank? What I can write, mass can be equals to rho multiplied with volume, density into volume, and that can be written as rho multiplied with volume is area of cross sectional multiplied with h, right? So this will give you the volume, and based on this density, if you will multiply, you can get these things. So finally you can get rho Fi minus rho F, that is equals to d by dt of rho area into height of the tank. So since I am assuming density of this liquid is constant, so I'll be taking this out of the differential, and also area of the cross section is constant for the tank. So I can write here rho Fi minus rho F, that is equals to rho A, and obviously d divided by dt of dh by dt. So density will get cancelled out in both sides. So finally you will be left with Fi minus F, that is equals to A dh by dt. So you can see that we are getting an ordinary differential equation, dh by dt equals to Fi minus F divided by A, something like that. Is that clear? So this is what we are getting at this particular moment. Now one more thing is that if I am talking about this here one more thing that becomes very important, that if I am talking about Fi bar, let's say, so if I am talking about Fi bar, that can be written as Fi minus Fis. So what is Fi bar? This is the in terms of deviation variable. Why I am writing these things? So when I am writing the Fi minus Fis, this is initial steady state value. Is that clear? Again, similarly, for this was for the inlet. For outlet, I can write F bar or F only. F, that is equals to F minus Fs, or F bar equals to F minus Fs, right? So this is for the outlet. So right now I am writing all of these deviation variables in terms of deviation variable. Again, if I am writing capital H can be written as H minus Hs, that is in terms of deviation variable. So these things becomes very important, right? Now if I am talking about the flow rate at the exit, F is the outlet flow rate. That can be defined as the height of the liquid in the tank divided by R. So what is H? H is height of liquid in the tank divided by resistance of valve, right? So this is how we can get it. So definitely here in this problem you can see that if the valve is there, then there will be a resistance associated with this, and that F will be equals to, here at the exit, F will be equals to H divided by R, where H is the height of the tank. Okay, this is very simple, and I hope this is very easy for you all now till now, and I hope you all have understood these things till now. So now we have seen that we got an equation that A dh by dt, that is equals to, we have got Fi minus F. So if I am assuming this one is equation second, and if I want to write at a steady state, so what I can write, A dhs divided by dt, that is equals to Fis minus Fs. So let's say this one is my equation second. So if I subtract my equation first and second, subtract equation second from first, so what I'll get, A d by dt of H minus Hs, that will be equals to Fi minus Fis minus F minus Fs. Is that clear? So now I can write A, and this can be written as dh divided by dt in terms of deviation variable, that can be written as fi bar s minus f bar. Is that clear? So in terms of deviation variable. Now what I can do here, so we can take a Laplace, right? So f bar can be written as now a dh divided by dt, that can be written as fi bar minus f bar can be written as h divided by r. Is that clear? So now if I'll take h this side, so I can write dh by dt plus h by ar, that is equals to fi divided r by a. Is that clear? So let's say if I am assuming this one is my equation second, taking Laplace transform of equation third, we will get what? Laplace transform of this differential dh by dt plus a and r is constant, so Laplace transform of h, that will be equals to Laplace transform of fi bar divided by a. So once we do the Laplace, so here you can write h into hs plus hs divided by ar, that is equals to that will be equals to fi bar s divided by a. Is that clear? So hs is constant, hs is output, so I can take it common, so s plus 1 by ar. Is that clear? So that can be written as fi bar divided by a. Is that clear? So finally what I can write, if you want to simplify it more, so I can write ar into s plus 1 divided by ar, that is equals to fi bar s divided by a. Is that clear? So since our transfer function will be equals to what? Transfer function will be equals to your output divided by input. So your output is your height and input is your this, right? So now I can write transfer function of tank, that is equals to hs divided by fi bar s, that will be equals to what? So it will go like that. So ar divided by a into ars plus 1. Is that clear? So here you can see a and a will get cancelled out, so finally you will be left with hs divided by fi bar s, that will be equals to r divided by ar into s plus 1. So this looks like a first order transfer function, but here only you have to define a time constant for the tank, that is equals to tau equals to ar. So I am assuming this tau a is area and r is the wall resistance. So finally the above equation, so let's say this one is equation 5, so the above equation will get transformed in this form. Let's say hs divided by fi bar s, that is equals to r divided by tau s plus 1. Is that clear? So this is the transfer function of a liquid level tank, right? So here you can see r is the resistance. So if you can recall the first order transfer function, so that used to be equals to gs equals to kp upon tau s plus 1, where kp is the gain. So what is the gain here? Gain for liquid level tank, that is equals to resistance r, and obviously time constant tau, that again I'll define here, that is the time constant tau, that is equals to area multiplied with resistance. So anyway, if you are able to get the value of gain, you will multiply it with gain in you will multiply with area, cross sectional area of the tank with the gain, and finally you will get the value of time constant. Okay, so that is fine. Now the thing is that, let's say you have hs divided by fis, that is equals to r divided by tau s plus 1. So let's see, if I am assuming if I am giving a step input at the inlet fis, that is equals to m by s, having a step input of magnitude of m. So hs can be written as now m divided by s into r upon tau s plus 1. So in the previous lecture also I have described these things for the mercury thermometer and this CSTR also. So now if I want to convert HS into HT, right? So what I'll do, I'll take Laplace inverse of HS, that will give you the value of HT minus HS in terms of deviation variable, that will be equals to Laplace inverse of m divided by s into r upon tau s plus 1. Is that clear? So here hs is the steady state value. So let's say if hs will be equals to 0, then what is the value of ht? So here I can write ht, height of the tank at any particular time, that will be equals to m into r into 1 minus e to the power minus tau t, sorry, t by tau. So the Laplace inverse I am not going to teach you here, because already I have completed this kind of thing in my first lecture, and I have discussed all of these things in very well defined way. There, if you will go to lecture 1 or lecture 2, there definitely you will get these kind of things, right? Okay. So this is how we can derive the transfer function of liquid level tank. So I mean, basically what kind of questions that can be asked from here? So let's say if at inlet they will give you a step input, something like that, and they will ask you the output response, something like. So let's say here, so they are going to give you at t, and here they are giving you a step input of magnitude, something like that, right? So let's say here that is 10 meter cube per second. Why? Because your input is this step input, and the value of r will be given, tau will be given, or cross sectional area will be given, and you are supposed to calculate the height of the tank, yt or ht minus hs. If hs is equals to 0, then that will be equals to m into r into 1 minus t by tau. So tau will be given to m is your 10, and finally you will be left with the value of st. So you will be able to calculate the value of st very easily. Is that clear? So this is how we can calculate this kind of thing, and this is not very difficult thing. So with subsequent lecture, you will feel at every thing that I am teaching here on this my YouTube channel, this will make you the concept very easy, and definitely you will be able to solve all of these questions in examination. So as far as my experience is concerned in process dimension control, so last 3 to 4 years I have scored full out of full in these things, right? So definitely this topic is going to help you a lot for this particular examination. Okay. So before ending the lecture, I would like to request you all, those who have not subscribed my channel, please do like and subscribe, and also share among your peers, so that those who are not aware of this particular channel, then definitely they will get to know the quality content over my channel. Okay, thank you, see you in the next lecture.